We're now ready to start talking about motion with a constant acceleration. We've defined displacement, distance, velocity, acceleration. So let's move ahead. And what we'll do in this video is we're going to obtain the equations necessary to tackle problems that involve motion with a constant acceleration. So first of all, let the constant acceleration be a. Okay, so this is the value of the acceleration itself. So what we see is that if an object, if a quantity is constant, does not change, then the average value of the quantity must be equal to the quantity itself. So very simply, we have that the average value of the acceleration is equal to a itself. So let's just put it in the box. Now we can use the definition of acceleration or average acceleration to obtain a very simple equation. We know that the average acceleration is equal to Vf minus Vi over the time interval, okay? But that is also equal to A now. So therefore, we can rearrange this as Vf minus Vi equals A delta t. And so we have this very simple, very important equation which says that Vf equals Vi plus A delta t. If you look at this equation closely, you'll notice that the velocity changes according to time in a linear fashion. So if you were to graph velocity versus draw velocity versus time graph for an object that moves with a constant acceleration, that graph will be a linear graph. It will be a straight line graph. So this would be some Vi, and also what we know is that the slope of this graph will simply be equal to the acceleration. The linearity of this graph is important in the next equation that we will derive. What we know is because the velocity changes in a linear fashion, and only because the velocity changes in a linear fashion, the average velocity also happens to be equal to the sum of the initial and the final velocities divided by 2. Now this is only because v is linear. If the velocity was not linear, then you cannot use this. So please be careful about that. So the average velocity happens to be the initial plus the final velocity divided by 2, only because the velocity is linear. Now we know also that the average velocity is equal to the displacement over the time interval. And so we can equate these two and obtain our next equation, which is delta x is equal to Vi plus Vf all over 2 times delta t. So this one is equation 1, this one is equation 2. Now we can use equation 1 and equation 2 and obtain a bunch of other equations, 3 more equations to be precise. But we'll do 2 of these and then you can just figure out the last one or the 5th of these equations. So what we'll do in order to achieve this is we'll eliminate a quantity. Now, if you look at the first equation has 4 quantities in it, Vi, Vf, A, and delta t. The next one also has 4 quantities, delta x, Vi, Vf, and delta t. Now, if we were to eliminate if we were to eliminate Vi, not Vi, we could do, sorry. Let us eliminate Vf between these two equations, between equations 1 and equation 2. We already know from equation 1 that Vf is Vi plus A delta t. So we can take that, plug it into the second equation, and obtain delta x equals Vi plus A delta t all over 2 times delta t. And this gives us, after a little bit of manipulation, it'll give us Vi times delta t plus 1 half a times delta t square. So this would be delta x, and this becomes our equation 3. If anybody is confused, just remember that you can add the two vi's, that gives you 2vi. I'll just write an extra step here, 2vi plus a delta t all over 2 and then delta t. So we can distribute the delta t inside and also then divide each of these terms by 2, and that ends up giving us this third equation. Let's look at let's also eliminate time now, but from equation 1 and equation 2. So we see that equation 1 tells us that delta t is equal to Vf minus Vi all over A. Now if we were to take this and substitute this into equation 2, we will get Vi plus Vf over 2 multiplied by Vf minus Vi over A. Now, if you were to FOIL this correctly, okay, so please do this. So if you FOIL the numerator, right, you will end up with Vf square minus Vi square, and then the denominator simply becomes 2a. We can rearrange this, move the 2a to the right hand side, and also then move the Vi square, and when we do this, we end up with Vf square is equal to Vi square plus 2a delta x. And these are the 4 equations that you will use a lot for the rest in the rest of this chapter. Now there is a 5th equation also that you should try to derive yourself, and in that equation you will eliminate Vi. Now if you look at each of these equations, you'll see that there are 4 quantities in every one of them, and each equation is missing one of the 5 total quantities. The 5 quantities are delta x, Vi, Vf, A, and delta t. Okay, and so if you look at equation 1 does not have delta x in it. Equation 2 does not have A in it. Equation 3 does not have Vf in it. And equation 4 does not have time in it. So one of the things that we'll do when we apply these equations to problems is we'll make a chart, and our chart will look something like this. So we'll have 5 quantities in our chart: delta x, Vi, Vf, A, and delta t. And then we'll fill this chart, and we'll recognize that in each situation there'll be one quantity that we will not need, and we will use that idea to basically go and figure out our equations. So when we apply these things to problems, we'll go over those steps and those ideas should be clear. But in the meantime, what I would like you to do is try to derive the equation for derive the 5th equation by eliminating Vi between the 2 equations, not Vf, sorry, I think I said Vf earlier, but eliminate Vi between equation 1 and 2, and then obtain that last equation.